Okay, so we're going to have a look at just a few questions here to test your knowledge and your understanding of optical isomerism from video one. So you might want to pause the video perhaps and go ahead and have a look at these questions, see if you can do them. Okay, and then once you've finished them, then you hit play on the video and check your answer. So explain what optically active is. So a lot of people say it's a carbon with 4 different groups around it. It's not. Optically active is to do with the fact that your substance can rotate plane polarized light, or of polarized light. Okay, so that's what optically active is. It's not okay. On the diagram above, circle the asymmetric center and the malic acid. So that's not the malic acid. We need to make sure and go to here. So we're looking for a carbon with 4 different groups. Now, we've got a carboxylic acid group at the top and at the bottom. So the quick way to do this is that the carboxylic acid carbons can never be optically active because they can never have 4 different groups around them. They can only ever have 3. We have a CH2 group here, so obviously a CH2 group could possibly have 4 different groups. It can have 4 groups, but if 2 of them are hydrogens, then it couldn't possibly be optically active. This group here is a CHOH. Okay, so yeah, we've got an OH, we've got an H, we've got a COH group here, and then we've got the rest of the molecule down here. So the optically active, or the chiral carbon, is the second one that I've just coloured in with a red splodge there. Okay, what name is given to this type of optical inactive product? Okay, well, so what it tells you up here is that if you read the first part of the question, okay, the malic acid is produced in industries. Remember I said in the last PowerPoint that when you're making these things in a lab, you make a 50-50 mix of the 2 isomers, the L isomer and the D isomer. They're made in a 50-50 mixture called a racemic mixture. So the answer to that is a racemate or a racemic mixture. Okay, and that's when you get a mixture which has got an optically active compound in it, but it doesn't rotate to the plane of polarized light because the 2 isomers are in it in a 50-50 mixture. And explain why the product of this reaction is not optically active. Well, that's just what I've just said there now, that you've the 50-50 mixture of the 2 isomers and they rotate plane polarized light in the equal but opposite directions. Okay, so we have a nasty little skeletal formula here, and we've got to find the chiral centers within it, so how many of them are. Right, so first thing, we have a carbon here, 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 here. We'll just fill them all in. Okay, and there's quick ways to rule out lots of these guys to save yourself an awful lot of hassle. Right, this line diagram, a line means a bond, circle then means that all of these carbons have another bond. Okay, so what we're essentially saying is every single carbon in this one here, in this structure, this hexagon, has got 2 bonds from the lines, and then this one has a hydrogen, hydrogen, hydrogen is all they can have left on them. So in other words, all of these carbons, okay, cannot be chiral. It's impossible. Okay, because they can only have a maximum of 3 groups around them. So very quickly, if we see a hexagon with a circle in it, it's called a benzene ring, and we'll get to that later in the course, we can rule them out. Let's go here. So though that's the same, they can only have 3 groups on them, those 2 carbons. Here we have a CH2. Anything with a CH2 couldn't possibly have 4 different groups on it if it is 2 hydrogens. Same here, rule that out. Okay, same here, rule that out. 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 Okay, here's a CH3. We can rule that out because a CH3 couldn't possibly. Here's a carbon here with an oxygen double bond on it, which means it can only possibly have 3 groups maximum on it. So again, we can rule that out. Alright, so anything left here is possibly going to have a chiral carbon. Well, let's see if we can sort of go through them and find what we have. So let's look at this one, the blue dot on it. Okay, well, it has this group, all of this group going that way. I'm not going to go through it all. It has all of this group going that way. It has all of this group going that way. Okay, I'll just draw arrows to show the 3 groups. And then it has a single hydrogen. So that has 4 different groups. So that's fine. That is definitely a chiral carbon. Let's go to another one that we didn't rule out. We didn't rule out this one. It has all of those groups going that way. It has all of those groups going that way. Neither of them are the same. Those groups going that way. None of them are the same. And then a single hydrogen. That's also a chiral carbon. So there we go. There's 2 so far. Let's go to this one here. It has this group going that way. It has this group going that way. It has this group going that way. None of those are the same as far as I can see. And it has a hydrogen. There's 3. That's ruled out. That's ruled out. That's ruled out. Let's have a look at this one. This is our last one. I think, is it? Or have I missed it? Yeah. So we've got 3 so far. Yeah, this is our last one. So there's a carbon there. It has a CH3 group on it. It has that group going that way. It has that group going that way. And it has this group going that way. All those 3 groups are different. So therefore, our answer is it has 4 separate chiral centers within that one compound. Okay, let's have a look at this one. Circle the chiral center in the structure above. Well, we have our benzene ring again, so immediately we don't even have to worry about those. We can just get rid of them all. We have a carbon here with a double O on it. That means it can only have 3 groups max. We can get rid of those. We have a carbon here with a double O and a carbon here with a double O. Okay, these carbons in the hexagon do not have a circle on them, so they may have 4 different groups. So this one here has got that group, it has got that group, but then it has H2. So does that one, H2. So it doesn't have 4 different groups. The only chiral center, the only carbon left now is that one. So it has that group, it has that group going that way, it has that group going that way, and it will have a single hydrogen also there. So it's got 4 different groups on it, so you would circle the one that I talked about. To find the term optical isomers, well, those are 2 isomers with the ability to rotate plane polarized light. Okay, it's not a reference to the fact that it has a carbon with 4 different groups. That's a chiral carbon. In fact, that's the answer to the first part of this question. Explain what is meant by an asymmetric center. That is now your carbon with 4 different groups around it. Okay, so just for 1 mark. Alright, so that's your chiral carbon. Explain what's meant by optically active. Well, we've done that about 3 times now. It's reference to plane polarized light. And we've got to go through this massive big structure and find the asymmetric carbon. Whew, right, let's go. Carbon here has a double bond on it. Couldn't be optically active. Carbon here, double bond. Couldn't be optically active. Carbon here and carbon here both have double bonds on them. Can't be optically active. Carbon here, double bond, double bond. Okay, carbon here must have a hydrogen-hydrogen. Rule it out. All these carbons are in a benzene ring. Rule them out. So you, okay, carbon with a double bond. Rule it out. Okay, let's go to the end. This is a carboxylic acid group. COOH. Any carbon in a carboxylic acid group can only ever have 3 groups on it. Rule it out. There's another carboxylic acid group. Rule it out. This is a carbon with 2 hydrogens. Rule it out. This is a carbon with 2 hydrogens. Rule it out. And finally we get to this little one here, which has a carboxylic acid group here. It has this whole big long group going that way. It has this group going that way, and it has, of course, therefore, because it's skeletal formula, got a hydrogen left over. So therefore, after all of that work, okay, but we should be getting quick at these now. That is my chiral carbon. Okay, right, last part then, a little bit of revision. We've got an aldehyde here, okay, and it asks you to draw 2 structural isomers of the above, which are ketones. So all I've got to make sure is that I've got 1, 2, 3, 4 carbons. I have hydrogens 3, 4, 5, 6, 7, 10 hydrogens and an oxygen, and I've got to have a ketone. So I'm going to go 1, 2, 3, 4. I'm going to pop that in there. So this is functional group isomerism. Okay, and there we go. We have 3, 4, 5, 6, 7, 8. Sorry, I'm missing a carbon. Actually, I can't count. I should have 5 carbons there. Okay, so I'm going to take another carbon and I'll just pop it there. So there we go. We have 10 hydrogens. We have 5 carbons, which I should have had up there, and an oxygen, and it's a ketone. That is indeed pentan. Sure you all know anyway. 2-one. and then all I would do, sorry, goodness me, I can't count, pentan 3 ohm, okay, and then very simply, I'm not going to draw it all out, just pop that into pentan 2 ohm, of course, dead easy. Okay, well, how many stereoisomers do I have of this compound? Well, the first thing I notice in this is I have a double bond, so I have a possibility of EZ isomerism, but I should notice about the double bond it has a hydrogen here and a hydrogen here, so there's no way it can have EZ isomerism, okay, because the two groups on one side of the double bond are the same. So let's go geometric. Well, I'm going to rule out that. Sorry, I'm going to rule out that, and I'm going to rule out that. It might be, it's either going to be A or it's going to be B. Let's look at optical, so we need to delve a little bit deeper into this structure to see if it's got optical. Okay. And then, oh, excuse me. Then we go to there, which has a hydrogen on it. So let's look for optical centers. I have carbon here with 3 hydrogens. Well, that's not going to be optical. I have a carbon here in a double bond. We should know by now that's not. Another one in a double bond. That's not. This carbon has a bromine, a CH3 group, a hydrogen, and a CH2 group. That is indeed an optical isomer. And if I've got an L isomer or one optical, I must have the other one. So therefore I have 2 opticals, no geometric. The answer is B. Okay, explain why this compound here exists as EZ isomerism. Well, the first thing you make mention of is the fact you have a double bond. Second thing you make mention of is you have 2 different groups on either side of the double bond. Okay, and that's what you've got to talk about. Which one of the following molecules can exist as EZ? So immediately we're looking for something with a double bond. Alright, so you may have to draw them out. Some of you may be able to work through them without drawing them out. Okay, I'll draw them out just to make life, hopefully that you'll see it. So I'm drawing A here for obviously. I get to a CH and then a CH2. Well, that can't have EZ because this carbon here has got 2 groups which are the same. Okay, I'll draw B up here. Okay, so B has a CH3. There's a CHOH and it has a COH. Well, it doesn't even have a double bond, so it can't be that. Let's move on to C down here. So CH3, CH2, CH, double bond to another CH, which is attached to a CH3. Okay, let's look. So we've got to focus our efforts around our double bonded carbons. This one has a hydrogen and a C2H5, so there you go. It's got those 2 groups different. And on the other side is a hydrogen and a CH3. It has those 2 groups different. That's our answer. Okay, let's have a look at this. So we haven't done naming these here things with CNs on there. We have done them in AS actually, so we'll have a look at it. We've got 4 carbons in the longest chain on a CN bond, so that's a nitrile. It is a 4 carbon nitrile, so it is a butane. Butane nitrile. We have an OH group, we have a methyl group that are not in the main chains, so we have 2 hydroxy. Remember, an OH group, low priority, gets a hydroxy, not an alcohol. 2 hydroxy, 2 methyl butane nitrile. What type of stereoisomerism is in this product? So the 2 types of stereoisomerism, remember, are geometric, which is EZ, or optical. That's our 2 options. Well, there's no double bond in it, so it's certainly not going to be EZ. It's going to be optical because that carbon there, if you look at it, has 4 different groups around it. So the answer would of course be optical. And then you're asked to draw the 3D representation of the 2 isomers. Okay, so I'll just do that if you remember from earlier. Okay, so get your system and just probably should have done that there. Sorry, my fault actually. Put the carbons towards the bond, yeah. And then I do my mirror, okay, and I do my mirror image. So making sure my oxygen's attached to my carbon up there. Oh, sorry, it's a CH3 group, and that's a C2H5 group there. So there you go, that's the mirror image. It's a bit rough looking, but hopefully you get the picture. Okay, and that is it, guys. So hopefully what we've done there, you've been able to follow and go through. You've got the first video to explain the theory, you've got the second video then to work your way through the past paper questions.